Now, as I mentioned last week, we're gonna do our test Friday. I think we're in a good place there. As far as the algebra and calculus is concerned, we already talked about how to do first derivatives, second derivatives with all our functions. So today we're gonna just look at kind of making sure we're comfortable with the first derivative and how that helps us with increasing and decreasing. And as you'll see here, we're gonna bring in the concavity, which will come from our second derivative. Okay, but hopefully what you'll see here is just making sure to connect everything to the right step. Okay, first derivative will give us where our function is increasing or decreasing based on that rate of change. The second derivative is going to be concavity. Putting the two of them together can help us identify where minimums and maximums occur. Okay. Now, one thing I hope that you took from last week was be careful with rational functions because you can have critical points from things such as vertical asymptotes. You also have to watch for stuff like absolute value or other piecewise functions that have cusp in them. I think one of the other functions that came to mind that can have a cusp that I was looking at, something like 2x to the 2/3, or I think it was, if I remember correctly. So if you think about 1/3, it does something like this. Well, if you put the squared in there, any negative value now is going to do this. So it creates a cusp there that can occur. Okay, so those are things that we have to be watchful for. Now, as far as this is concerned, though, I'm going to focus on mainly polynomials right now, just to kind of keep it in, like, what do I do with this test? I think I put a practice test up. It should be available now for you on Canvas. If you don't see it, just let me know so I can make sure to fix that. Now, as far as dealing with this particular function here, always pay attention to what you're given. So I have f of x, so this is my original function, and it says list all relative extrema as well as any points of inflection. Relative extrema means, hey, I'm going to definitely need at least the first derivative. Okay, when you see points of inflection, that's going to be our second derivative. Okay, so what we first want to do with our function is go through and differentiate. And because it asks for both extrema and points of inflection, we definitely want to get to first and second derivatives. Are we okay though with dealing with that as far as the power rule derivatives is concerned? Now, the first step to deal with this is definitely find critical points. So what do I set equal to 0 to get critical points? All right, so we definitely want to make sure to remember that. Hey, I'm going to take my first derivative, set it equal to 0. Hopefully take some of the stuff that we looked at last week. Yeah, sometimes I'm going to have to be creative in how we solve, right? So be prepared for, factoring by grouping. You saw we did the one with synthetic division here. Hopefully you'll see like, hey, both of these terms end up having 4x in common. So that's kind of nice. So I can factor that out. And then how you solve it from here is up to you. Just make sure you see you're going to have one solution from here and two solutions from here. All right. You can continue to factor that. I just did a quick square root. So don't forget when you do square roots to put your plus or minus sign. So as far as critical points, we have -1, 0, and 1. Now, does that help us with increasing, decreasing, just having those values? Or do we need more? Right? So understand the critical points are where we have horizontal tangents possible. We have restrictions possible. Since this is a polynomial function, we could confidently say, hey, I have 3 horizontal tangents on this graph possible. We'd have to look into it a little bit to understand if it's 3. Based on this being x to the 4th, I'm imagining something that looks like such, a kind of a W shape. Okay, that's my picture right now. It's not a U because it's x to the 4th, but both ends are going to go up. And I have 3 turns taking place possible. Okay, these values here would be -1, 0, and 1. Just kind of highlighting this. We don't know exactly where they're at as far as how high or low they are. But hey, that's where we go further with like plugging values in and dealing with stuff. But is everyone okay with what the negative 1, 0, and 1 represent? Now, with that said, let's bring this stuff over here with us. That was this piece here. So whenever you use a square root to solve, just make sure you remember, hey, plus or minus, right? That's one of those that we just have to be careful not to forget that step, right? Especially in our class, y'all understand it's easy to miss stuff like that, right? So it's always important, like, hey, this was x cubed when I did the derivative. So I was looking for 3x values. So that might always be kind of a where did I miss? Oh, hey, that plus or minus. Okay. With that said, just to help consolidate real quick, we have our derivatives. We found our critical points here. The one thing we can get to now is go ahead and let's find out where our function's increasing and decreasing since we already have our critical points. Okay. So this is where we kind of left off last week with saying, hey, let's go draw a little number line real quick. And the values that I'm going to put on this number line are going to be -1, 0, and +1. Give myself a little bit more space here. Now, make sure you see that for each critical point you have, you're going to have an interval on either side of it. So what we need to look at are these intervals now to determine if it's increasing or decreasing. Okay. The one nice thing about this, remember, all we need to do is go see what's going on with the derivative. If the derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. So picking values is all we need to do here. We could do something like -2. We'll do -1/2, +1/2, +2. Just understand you will be stuck using the 1/2, okay? This is also in this situation where, hey, use your calculator to help make stuff a little bit quicker. Okay, this is definitely plugging in some values. I do not expect you to do these by hand. It's Salem and Donovan, correct? Salem, it's Donovan. Sorry, my brain is not functioning today full. Calculate. So for those of you walking in, we were looking at this problem here. So as you write down the instructions, just know we're on the first derivative. Since we have critical points, we can go find the increasing and decreasing, okay? So we have 4x cubed minus 4x. And I'm going to just plug in each of these values that I chose. Now, do you have to use -2, -1/2, 1/2, and 2 here? No, as long as it fits interval, any number of work. If you want to do -0.1, just make sure you put it here on this interval, okay? So just keep that in mind. But for this one here, I got -24. What that means to us, it doesn't matter what value I pick on this interval, any value is going to give me a negative sign, okay? So we know that from as far as increasing and decreasing for this function, it is decreasing from -infinity to -1. Okay. Now, being a polynomial, we should kind of assume now it's going to switch. Okay, we can kind of expect it to. That's not always going to be the case because it depends on multiplicity and everything that goes into that. But hey, let's see what happens when we plug in -1/2. All right, for here, I got a positive value. So no matter what value I put in here, it's going to be positive. So that means to me that, hey, from -1 to 0, it's increasing. Plugging in +1/2. I got negative. So any value I pick here is going to be decreasing. Then the derivative is always going to be negative. So just make sure you see here again in your notes that, hey, we're taking each of these values and plugging them into the first derivative function. All I care about is the sign because positive is increasing, negative is decreasing. Okay. Then plugging in the positive 2, I get a positive 24. Now, with that said, that gives us everything we need. So we have multiple intervals here. Trying to remember right now. Has anybody done one of these on the homework yet? The one I was working on today put a union symbol here. Yours might do a comma. I can't remember what the textbook does on the Pearson side. So I'm going to put union symbols because that's what the practice assignment's going to make you do. That was the problem that I coded. Okay. If it's a comma, just put a comma here. But what we're saying is, hey, I had two intervals for increasing, right? The first one is here. The second interval is over here. Okay. Because when I pick a value and plug it in the first derivative, it's positive. So just make sure you see those, a bunch of parentheses involved with here because we can't actually use a specific value for increasing or decreasing. The second part here then is going to be the 0 to 1. The one thing I will point out here is make sure you cover your entire domain. So this is negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. So we've covered that domain. Everyone comfortable with that? Any questions or concerns? Now, things I would highlight here is make sure you take note that there's a change that occurs here, and that same kind of change occurs here. If something goes from decreasing and then starts increasing, what type of extrema do we have possible? It's a possible relative minimum, right? There's a relative minimum. That should be extrema, not extreme, sorry. So understand that we're expecting some minimum values here. At a relative max. Now, what changes with this piece here that makes me say relative max, right? Well, hey, it's going from increasing to decreasing. It's kind of the top of the mountain. Now, the word relative is very important here. Okay. The reason I'm using the word relative is because as we look at this little sketch I did, what are these two things going to do? Seem to grow and go up forever, right? So this is definitely not the highest point on the graph. Now, it could be possible that one of these two, though, is the lowest point of our graph. Okay. So one of the things that we will start to look at, and that's going to be kind of where we're going in a second, is how do we start getting to what we call absolute minimums or absolute maximums? This will be important because, like, say you're working with a situation and you want to find the maximum value possible. Well, hey, now we have a way to deal with this. The first derivative and the second derivative are going to help us work our way through such information. Okay. Now, are there any concerns though where I'm getting that from dealing with this first derivative? Everyone's okay with that in the interpretation of increasing and decreasing? Everyone's good with why I'm saying relative mins and maxes. Okay, well, let's go look at this from the perspective of that second derivative now. Oops, got the direction, sorry. So as far as the points of inflection now, This is where our second derivative comes in, and that's also going to be helping us with concavity. Okay. Now, as far as this graph is concerned, just because we're working with a polynomial, I'll go back to this kind of quick idea here. What we'll see is this portion here, we call concave up. All right. One of the ways that helps me remind it is like if you poured water in here, it would hold the water. So anytime you have something concave up, it's making a valley. Okay, that would hold water. This piece here then is concave down. Okay, and the idea there is if you try to pour water into this, it's going to pour out the water. Okay, concave up, valley, concave down, we're thinking top of a mountain. Okay. With that said, then the points that we want to find is where does that change occur? Because if you continue with this graph, hey, look, this whole right side looks like it's going to be concave up too. So where do these changes occur to help us see that? Well, that's where the second derivative is going to come in and help us. And those what we're going to call points of inflection. Okay, so if I go over here and I set the second derivative equal to 0, how many possible solutions will this give me? Well, it's x squared, right? So I'm expecting 2 solutions. Well, hey, didn't I highlight 2 points just now where this could occur? Okay, so if I go to solve this one is not going to be as nice as other ones, right? So add the 4 divided by 12. Okay. Make sure you see there, I'm getting the 1/3 from dividing a 4 out for both of those. When I do my square root here, though, it doesn't work out as nice because I'm going to be left with plus or minus the square root 1 over the square root of 3. You also might see this written as square root of 3 over 3. Okay. Now, what you'll see here, though, is kind of looking at that 0 value. This is the same distance to the left to right of 0. Okay, so there's some kind of symmetry going on here, possibly as far as the inflection points around that middle critical point we had. Okay. Now, what we'll find is that, hey, these are possibly points of inflection. We can test this by doing the same thing we did the first derivative. Let's go build the number line. And the numbers we're going to focus on now is going to be this negative square root of 3 over 3 and the positive square root of 3 over 3. And please understand, if you want to leave it as 1 over the square root of 3, I don't think I would make a big deal about that because your calculator can handle it either way. Okay, but when you go to like the textbook, you're probably going to see it in, that rationalized form. So just make sure you understand that. What's a value we can plug in between these two numbers? We could definitely do -1. No, not -1. Nope. If you look at the square root of 3 over 3, these are going to be about 0.57. Okay. So -1 would be great here. Maybe that's what you're saying. If you meant that, I'm sorry. But in between them is what I was looking at. Just make sure you see this would be a place. Make sure you use 0. Okay. Is what I was going to show. The extremes, though, 1 and -1 would be great. Sorry. Now, what function should I be plugging them into, though, if I'm trying to test for points of inflection and concavity?
-1.
The second derivative. Right, this is where now we're saying, hey, the second derivative is our focus, so let's go plug in -1 into that second derivative. Okay. That gave me a positive 8. So just make sure you understand again, it didn't matter what number we picked in there, the result is always going to be positive. Okay. If I plug in the 0, we're going to get -4. So these would be negative no matter which one I pick. And if we plug in +1, we're going to get a positive value, output it again. You'll see here that for that second derivative, that give us a positive 8 again. Now, what that means is we had some changes occur again, right? So these both are going to be inflection points. One side is concave up and then it switched to concave down. So we would say, hey, I have 2 points of inflection for this function here. Okay. Not only are we able to state the 2 points of inflection, but we're also able to give the intervals where this function is that concave up and concave down pattern. Okay. Now, what you'll see here is this is another thing that kind of highlights the fact that we have some extrema occurring. Okay, there's one relative extrema possible for each of these intervals. If it's concave up, you have a relative relative min possible. Concave down, you have a relative max possible. Okay. So dealing with the graph itself and bringing the two things together would help us say, yeah, those three things were relative extrema that we identified. Okay. But just make sure you see from here, once we get to this second derivative, we're able to say, hey, I have points of inflection at x equal to the plus or minus square root of 3/3. Both of those points are fine. Okay. If you ever need the actual values, plug them into your function. Okay. As far as dealing with this is concerned, we would say it's concave up on the intervals of negative infinity to negative square root of 3/3 and square root of 3/3 to infinity. The function is then concave down on that interval that's in between them. Now, just kind of look at this graph here. What do you notice about the shape it makes? How many turning points occurred? There was 3 turning points. We expected that though, right? Now, the thing that calculus allows us to do is better describe those turning points, right? The turning points that I'd focus on would be these two here. Those are both what we'd consider relative mins. Okay, what you'll find is based on this function, they actually share a y value. So the minimum value of this graph would be -4. Okay. This here is another turning point. Well, we recognize this is a relative max because the graph was increasing and then it started decreasing. Okay. One other thing I would point out is what do we call this piece here again? Well, that's our concave up, right? There's an inflection point, which wouldn't necessarily be easy to get to kind of just looking at the values because it was a square root of 3/3. Okay. The only things that were nice was like dealing with this x-intercept here and the fact that it was x squared, which is why you saw it consistent when it went to the first derivative. Okay. Now, as far as these intercepts are concerned, yeah, they're not going to be nice values, but we can get to them if we needed to. Okay. Thankfully, the extrema were nice to get to. Okay. As far as the first derivative are concerned. Okay. And you can see here, it actually highlights those key values for us where like we looked at it, I said 5.7. I didn't round properly apparently because it's 5.8. Okay. But you'll see here, we could highlight those points as well for whatever reason, didn't like the negative. Everyone feeling okay with that though and how it applies to that graph? Any questions or concerns with this first problem? what I hope you see is this goes kind of combining stuff that we learned in college algebra as far as inequalities is concerned with derivative functions. The one thing we need to take from this, the first derivative is for increasing and decreasing. The second derivative is for concavity. Bringing those together, we can definitely start talking about the relative extrema. Okay. But the next step, as I mentioned, is let's talk about absolute extrema. When we start moving forward with this, we don't always want just the relative information. We're always going to have some type of boundary points that kind of limit what we're focused on. Like typically, we're not even going to worry about negative numbers, right? We're looking at a profit function. So we will have a minimum value to a maximum value, right? Things that would come into mind if your revenue function is based on how many units of something you can produce to sell, you're going to say, I can produce zero, which would be zero revenue. But then you might have some type of maximum there that like, hey, we know we can't produce more than this and maintain whatever quality or even get past that based on what we have, right? So those would be your minimum and maximum input values you can work with. Here, I have a function, and this is going to be our limited domain. So what you're seeing here is that when I look at my x values, I'm going to go from -1 up to +8, and that's it. So if we were going to do a quick sketch of this graph, I would need to make sure to say, hey, I want to make sure to limit my graph in that way. Furthest to the left I'll go is -1. The furthest to the right I'm going to go is +8. Now, this creates a situation now where I will have possibly relative extreme on this interval, but I will definitely have absolute extreme on this interval. Okay. What we're going to find here is we're going to need to look at our critical points as well as our boundary points. So one thing I would say is since we're going to need critical points anyways, let's go get our first derivative. So what did y'all put for that?
-4.
What's the derivative of this 8x squared minus x cubed? You good?
16x minus 3x squared.
Gotcha. Everyone says they're feeling good with that, right? Now, with that said, since we're trying to find extrema, whether it be relative extrema or absolute extrema, we definitely want to go say, hey, where are my critical points at? So I'm going to go find my critical points by setting this first derivative equal to what? 0, right? We're using those horizontal tangents to help us know where possible turning points are taking place. So here I have 16x minus 3x squared, and I'm going to set it equal to 0. Well, the nice thing about this is I can just factor out an x. A little bit nicer than even the one that we just got done doing, which means I have two values I need to focus on, x equals 0 and x equals 16/3. Careful with your signs on that second one, right? So as a subtraction, the result will be positive. Now, what I would do with this here is build my little chart, just kind of give me an idea how I'm about to draw my graph. Okay. This is just me saying, hey, I can do this quickly, so let me get a quick understanding what's going on with my graph. In fact, let's just go plug in 1. What's that going to be? 6. And we can do -1. Now, we don't really want to do anything less than -1 because that's not a part of what we're working with. When I plugged in -1, I got -19. I plug in +1, I got 13. When I plug in the 6, I get a -12. Now, keep in mind, each of these values is coming from that first derivative. I'm plugging each of those values I highlighted down here into my first derivative, okay? Now, if the problem wants you to, make sure you go in and state like what interval's increasing, what interval's decreasing in interval notation. For us, we could do a quick check, just say, hey, it's decreasing, it's increasing, and then decreasing. So what's something that I can interpret from that value, from that quick glance? What would y'all say is going on at x equal to 0? Right, there's a relative min at 0. And that means at the 16/3, there's a relative max. Okay. Now, you don't necessarily need the graph for this, please understand that. But having this information kind of helps us, because what we need to go now and move forward is let's plug in our values and determine if these are the absolute min or absolute max. The way that we handle this is, now that we kind of know what to expect with these numbers, is we can go start plugging stuff in. So we'll go plug in f of 0, we'll plug in f of 16/3 to get those baseline values. But then what we need to plug in also then is going to be the f of -1 and f of 8. So anytime you're trying to find absolute extrema, you want to plug in your relative extrema that we got from the critical points. And then you're going to plug in your boundary points. Okay. Now, the one that is nice here is I'm just plugging in 0, but keep in mind, what function did I just say I'm plugging all those into? All right, this is going back to my original function now. Now plugging in 0 is nice, okay, because hey, there's no constant term, so it equals 0. But know that, the other one's a little bit more work involved. If I plug in -1, it gave me 9. If I plug in 8, it gives me 0. Plug in 16/3. It's giving me about 75. Well, 75.9. If I go plot these out as best I can, we'll have something that's here. Something about right here. 16/3 is just a little bit more than 5. So I'd put about right here. And then f of 8 is 0. What we can see though from the behavior of our graph, it's going to do something that looks something along these lines here. Okay. That's just me taking the first derivative work that we did and trying to bring it over here. Now, what can you say about this value here? Definitely. Because I shouldn't even included this, sorry. Those are our endpoints. I'm not passing. What's the one thing we can definitely say about this value here?
Maximum point.
That is a maximum. Now, is there any point going to be higher than it on this given interval? No. So this is where we would actually need to then interpret this as, hey, there's an absolute max. And then this is where we would do a couple things. Since we plugged it in to determine this, we would say there's an absolute max of, we'll say 76, just for the sake of rounding, an absolute max of about 76. Okay. And it occurs at x equal to 16/3. Okay. It's very important that we're careful with how the problem is worded, especially going to be on the test or the homework. Is it wanting you to tell it where the absolute max or min occurs at, or does it want to know what the minimum or maximum value is? Okay. It's a little bit different about the minimum perspective though. What do we notice about the minimum values here? So the 75 definitely is set apart by itself, but when I go to the bottom of the graph, what occurred twice? Zero, right? So we have to be careful and understand that I got a minimum at two different points here. Okay. So if I'm looking at x equals 0 or x equal to 8, they both are going to be the lowest possible value given in this problem. Okay. So we'll see that we have some absolute mins. At x equal to 0 and 8. And the value of that minimum is 0 itself. Okay. Now, the thing that you have to see here again, to be able to find an absolute extrema, you have to have a clear distinction. This is why we like quadratic functions, right? A quadratic function, that U shape, it's always going to have an absolute min or max. But the limits would help us better explain the end of that graph, right? So like when I bring in the limit as x goes to negative infinity, and limit x goes to positive infinity, we can better explain that. Well, if we have endpoints to our function, now we have to weigh to say, hey, the two edges are being limited to these values. So anything in between them is either going to be an absolute extreme or absolute min, okay? When we deal with that, the idea of the extreme value theorem is kind of coming to mind, right? That something's going on. The values as we go between A and B, right? We can look at those and know that as long as the graph is continuous, of course, right? If this wasn't continuous, that'd be a whole different discussion. But because our function is continuous, we're able to identify these values. Now, this is where we're going to see that an example of how this would benefit us. Why would we need to know this? Now, I'm going to go through this one a little bit more quickly. What makes you see here, this is kind of going back to some of the stuff that we looked at before, right? Hey, we have a revenue function, we have a cost function. We should definitely recognize the R of X and C of X as revenue and cost. And it says find the maximum profit and the number of units that must be produced and sold in order to yield this maximum profit. And just assume we're just in dollars as far as the output for revenue and cost. Okay. Now, one of the key words here again is profit. What does that tell me I need to do to start this problem? I've got to go do the work of getting the profit function, right? So we definitely have to remember that, hey, the profit function here is going to come from our revenue function minus our cost function. Now be careful with your parentheses here. We're subtracting the entire cost function. So 52 minus 22, what's that going to give us? 30. Something that looks like this. Now, in order to find the maximum profit, what do I need to do to this function? How do we find maximum values of a function? We're going to take a first derivative, right? Once we get my first derivative, I'm going to then be able to go find those critical points. And be careful, that 1/2 doesn't seem nice, but when we take the derivative, 2 times 1/2 is just 1, right? Just don't forget your negative there. But now we want to go find those critical values, the critical point, right? So we're going to set this derivative of the profit function equal to 0. We find that that critical point occurs at x equal to 30. Now, all we need to do is go in and say, hey, is this a minimum or maximum value? Okay. Well, that's where we go back to that little quick table. This is something that can be done quickly, just kind of visualizing and checking. 30 is our focus, so let's go plug in 0. And let's go plug in something like 40 just to make it easy. But remember, we're plugging this into the derivative function. This is us saying p prime or whatever value I pick. Well, if we plug in 0, we get 30. So this is going to be increasing here as far as our original profit function. If we plug in 40, though, we get -10. So now it's decreasing. Well, does that agree with a maximum value? Well, yeah, right. If it's increasing and then decreasing, it's going to look something like this. So we know that we have a relative max at that value. And because it's quadratic, again, we can be confident that that is the absolute max of our function. Okay. What you'll see here is, guess what happens when you try to take a second derivative? What's the derivative of this statement? -1, right? That right there is going to tell us that our function is always what? Concave down, right? Because it's always concave down, there's only one possible extrema, therefore we can call it the absolute extrema, right? So we can go say, hey, there's an absolute max at x equals to 30. Now, what does that mean to us? Well, hey, you have to produce and sell 30 units to yield the maximum profit. How do I find the maximum profit? Well, let me go plug 30 into that function, right? So the next thing to do is go say, hey, the max profit that we should expect is going to come from P of 30. So we used the first derivative to find the value of 30. Okay. I did a quick little first derivative test on a number line just to see what it's doing to the left and to the right of the 30 from the first derivative perspective. Okay. As you can see here, doing the second derivative could also say, hey, this is always concave down, so I know that's an absolute max. But definitely want to make sure, again, we're comfortable with our calculator. Go plug this in to our profit function.
The first function, right?
This one, yeah, this one here. Definitely use the one you simplified, right? Don't, you could technically use this, but this is going to prevent fewer errors by using that simplified version. So I got 451, which means my maximum profits can be $451 when I produce and sell. What do they call it? Just number of units. Okay. What I hope you see here, though, is this is a quick way to start highlighting stuff like this. Another thing that you'll see here, what I would hope you find, this is a lot easier than trying to go find the vertex by using negative b over 2a, right? And then having to plug that value in. By using a derivative, we just had to do 2 times 1/2. And then make sure to decrease the exponents to get rid of the x, okay? Using the second derivative again, just as confirmation was, hey, it's always concave down. I know this is an absolute max because there's no change in concavity here, okay? Being a polynomial function also kind of reassures us in that as well.
Question. How did we, do that, RX, negative, CFX, RX, CFX?
Talking about this piece here?
Yes.
Yeah, so the profit function will always be the revenue function minus the cost function. Remember, the idea there is how much money am I making and how much did it cost me to do that? That will definitely be something you need to know. Is how do I get a profit function, okay? Another thing I'd point out there, if it says find the maximum average profit, what do you need to do to your profit function? Divide by X, right? So if it says average profit, just remember, take your profit function and divide by X. So make sure you always are reading what does it want us to focus on, okay? One of the things we'll see you guys move into next week after this second test. Third test, sorry. We'll start talking about different terms of concern. Right now, I feel like total profit, max average profit, or I could throw either one of those on this test, okay, and then ask you to maximize. Okay, because that's going through here and saying, hey, we know how to find a first derivative, we know how to find a second derivative. We've now looked at how to interpret those, okay? Well, here's a good, to me, application of that is well within the range of what we've discussed. Now, when we come back next week, we'll start throwing stuff in there like marginal profit and stuff like that, marginal demand and stuff like that, as well as related rates, because dealing with increasing, decreasing, maximizing, we'll have all kinds of different ways to view this perspective, okay? But that is all we have time for today. So we'll go ahead and stop here. If you have questions, feel free to stay. If not, I got everyone for attendance. So have a good day and I'll see you on Wednesday.